Great. Welcome everyone to the first afternoon session. I'm David Wormelder from MarkLogic, and we're sponsoring this track today. So it's a great pleasure to introduce the speakers. Our next speaker is Dan McCreary. Dan is a local author. He is a consultant and technology evangelist with a focus on helping firms take advantage of modern data management technologies. He's worked at Bell Labs, Steve Jobs' Next Computer, as well as founding his own consulting firm of over 75 people. His background includes topics such as high-performance computing, programming languages, databases, and XML standards. He is co-founder of the NoSQL Now conference, which is a very large and successful conference, and co-author of the book Making Sense of NoSQL by Manning Publications. And while Dan was an independent when he put this presentation together, he's also a colleague of mine, having joined MarkLogic on Monday. So I welcome Dan on both counts.
Thank you, David. All right, so what we're going to cover here is a little bit of what is NoSQL, how do we define it. We're going to go through the 6 NoSQL architectures, one of which, by the way, is the traditional relational databases. We'll talk a little bit about how they're different, sometimes similar as far as interfaces and sometimes dramatically different as far as how they scale out. We'll talk a little bit about the types of business problems that they solve and a little bit about how to learn more. The slide I just put in there for reference pretty much what Dave mentioned. And I just wanted to mention that what I'm going to give you today is about a 45-minute section out of the 40-hour curriculum that we developed for the book. We developed this for large companies that were trying to make the transition from a mono architecture, where everything was relational, to much more what we call the polyglot, where you have many, many different architectures. And so we're going to just kind of give you a skim of a taste of the book. But I thought, since this is a Minnesota audience, I should give you a little context of how I got into this. So I want to take you back to 2006. I was a data architect over at the Minnesota Department of Revenue, and my job was to get 87 counties in the state of Minnesota to all agree on the data elements for exchanging property tax data. And we started out, it was pretty easy. We said, do you mind if I use the federal models for data? And so I used the National Information Exchange Model, NIM, which I had designed and built a lot of them at Crimnet. Then we started to go in and build the schemas. And I'm going to tell you a story about this and the schemas and how the schemas evolved and how it got me into the NoSQL world. And it's really a story about agility and technology adoption. So has anybody ever heard of a CRV, Certificate of Real Estate Evaluation? Anytime any 2 people buy or sell property in the state of Minnesota, if it's over $1,000, you're required to fill out a form. And that form is used as a statistical basis for evaluating the properties. And this data is complicated. It has buyers and sellers. It has plots. You might be selling a chain of restaurants with parcels in many different counties. And so each of these little boxes would open up. This is a schema diagram. And if I was going to then manage it, I had to define and build a metadata registry. So here's all the metadata registry elements that we created. And then we, for each of these, would go in and write definitions so that everybody would understand them. And so we were doing all of our good semantic development. And then we could take this schemas and run a transformation on them and create the forms. Right? XML schemas have a lot of the information, so if there's a pick list of all the values, you automatically generate a drop-down list. So after about 8 months, we were then ready to save the data from our forms into the database. All right, so, and it's a complicated form. There's about 45 SQL insert statements that we figured we'd have to generate in the right order. And we were all ready to do this, and I was going to build an object model in Java. And we're going to take each of these XML things, we're going to break it up into Java components, we're going to use Hibernate, and we're going to store all those components into the individual tables of our relational database. We had about 6 months scheduled to do this, and I was ready. I was a great data modeler. I had taken all the ER modeling classes, and I had done this over and over, and I was really good at it. And then I went on the line one day and I was chatting about our schedule. And this guy said, you know, you could do that with one line of code. And I said, I don't believe you. I'm an ER modeler. I know how difficult this is. I know how this data will change. The databases are going to change. We have to be able to have all this middle tier to decouple it. And he said, no, you could do it with one line of code. So I didn't believe him, but over the weekend I went and Googled it. I found other people doing it. I downloaded some software, and sure enough, it worked. One line of code took 250 data elements and immediately stored it into an open source relational database at the time. And I could immediately query it. Right? So how many people have been on a software project where a 6-month project could be done in 5 minutes? All right? And from that day, I started to question a lot of the things that I had been taught. I started to question whether everything had to be in tables, whether I had to store things in rows and columns, whether I had to use joins. And I started to study other people who are doing it. I went to other conferences, and I really started to understand the fact that I was not taught everything that I should have been taught in my database classes. I didn't really understand the concept of objects and object models. And I was angry because I should have known this. As a solution architect, isn't our job to be aware of the best, lowest cost solutions to solve our business problems? So I was angry at myself for not being aware of this. So I started to blog about it. I started to create wiki sites that documented it. When I went to conferences and talk about it, I was very frustrated because I'd go into a room and talk about the wonders of XRX, and I'd get deer in the headlights look. Nobody would understand what I was talking about. So in frustration, I said to Tony Shaw, the guy who runs the Dataversity conferences, let's start our own conference where we can bring in the evangelists that know this, that understand it. And it wasn't just about documents. It was also about graphs, and it was about key value stores. And we've had a very successful conference. We had 1,200 people at the last one. We got a nice offer to publish a book. And even today, we see if you go and Google RDBMS and NoSQL, it's still a very, very popular term, and it's growing in popularity. The NoSQL universe is very complicated. There's a lot of startup companies with a lot of new ideas. There's a lot of innovation. There's a database called TechCrunch, and I run queries on that database. It's a list. TechCrunch stores all the venture capital funding that have gone into startups in the Bay Area. I track dozens of NoSQL companies, and I'm tracking right now $2.3 billion of venture capital in these companies just in the last 3 or 4 years. So there's a lot of money in it. The other thing about NoSQL as you go to these conferences is there's a huge amount of jargon. And what they do is they take words that you may be familiar with, and one of my examples is consistency. Everybody hear of this concept of ACID consistency? Right? We know what the word C means, consistent in transactions. Begin transaction, do an insert update, and then you're consistent in your reports. When you think about a distributed cluster, they use the word consistency. They mean something totally different. They mean when you're doing reads, 2 different reads in a cluster, you're going to get consistent values from that cluster. So the words mean totally different things. So what we want to do is take a book, and we start out very slowly in our book, and we say, this is the relational model, right? We are familiar with row stores. You know, you add 1 row at a time. We have columns. Columns have constraints. You have to have consistent data within all those columns. And the way that you create reports is you do joins between these tables. The nice thing about joins is that you're always creating a consistent table in, table out structure. The problem with this is if you have customers on one node in a cluster and products on another node, and you need to do a join, you need to move data between those 2 nodes. So there's a fundamental scalability problem when we have architectures that are join intensive. There's another model called an analytical model. Analytical model is where we have a centralized fact table. That's a single table where every transaction, every event is a fact. And then around that we have dimensions, time and product and a category and promotion and store location. And that's ideal if you're doing historical analysis and you want to pre-compute sums and totals so that business analysts can count things. So this is kind of the existing way of the world. We talk about it in the first couple chapters. And then we layer on that the 4 new data models that NoSQL has introduced. These include key value stores. Key value stores, some people don't even think of it as a database. They think of it as a data structure, right? All you have is a simple key and then some opaque blob. I have it in black because you can't really query anything inside the value. And the operations are simple. You can insert a key value pair. For a key, you can return a value, and you can delete a key value pair. That's not much of a query language, right? But the interesting thing is with that simplicity, it allows you to scale out and have other high availability features that you simply can't get by using these other models. So key value stores are beautiful in their elegant simplicity, and that means there's other dimensions of databases that you can push. There's a related thing called a column family store. It's kind of like a key value store, but the key has 2 components. It has kind of a row and a column, and you put those together, and that comprises the key. But it does give you more things that you can query. So if you're doing an invoice date can have 1 consistent column, so there is a little bit of data modeling involved in column family stores. The next one is graph stores. Graph stores is where everything in your database is a directed graph. Everything is a node and an arc and a node, and they're all hooked up together. These are ideal when you have lots of relationships, when you want to do social network analysis, when you're doing shortest path analysis in maps. There's many other areas that you wouldn't think are relationships sensitive, but they actually are solved very well by graph stores. And the last one, which is my personal favorite, is document stores. Document stores think of an XML file or a JSON file. It's a hierarchical structure of documents. They all have leafs and they have nodes, and they're all hooked up together as a logical entity. Now, the interesting thing about this is each of these systems does certain things well. If you're doing a transactional system, and you want reliable ACID transactions where you can do begin transaction, end transaction, and you want fine-grained security, a relational model is actually a pretty good model. And nothing I say should take away from that in this presentation. But if you wanted to take something like Wikipedia, load it in your database, tag every noun, and then count the number of nouns in Wikipedia, and then do inference on things around that, maybe a relational database isn't the right way to do that. Maybe a document store with graphs. Things like Watson, right? Watson was a natural language interface to asking questions about a large base of knowledge. So depending on your business problem, different models work well. And that is really what our book is about. So let me ask here, how many people here are familiar with the relational model? Okay, 100%. I didn't see anybody who didn't have it. How many people here have done an analytical model? Okay, more than 2/3. How many people have used a key value store? Okay, a little less. How many people used a column family store? Just 1. Okay. Graph store? Just 1. Here's a guy who's done a lot. And then document stores. Okay, more document stores. Right. Okay, so what we see is we don't have a uniform distribution of experience over these 6 models. And that's the problem that we have in Minnesota. Let me ask, if you work for one of these companies, Google, Yahoo, Amazon, Facebook, LinkedIn, or Twitter, what percentage of the data that they're managing do you think they have in relational databases? Just ballpark. Less than 1%? Anybody else? Okay, I think that's pretty close. I'd say between 1 and 5% is a typical estimate. What about Minnesota? How many classes have people taken here in SQL? Most people have. Most people have had relational ER modeling classes. But how many people have taken a class at the University of Minnesota in document modeling or in graph databases? And the answer is the business opportunities that we'll be able to address in Minnesota are focused on probably 1/3 of the design space. 2/3 are being taken away from us by these companies in California. So this is a problem, and this is what we're trying to address in our book. So why is it we call it NoSQL? And the answer is it's a historical artifact. The guys that got together for a while that were doing this, the things they had in common was that they weren't using SQL. But in fact, nowadays, most of these systems, in fact, have SQL APIs. Right? If you're going to do Hadoop, you've got Hive. Hive looks exactly like an SQL interface. There's one thing. It just doesn't do joins well at scale. Right? But you're still doing select column, column, column from table where something is true. But you're only using a subset of everything that. So we don't call it the NoSQL. We call it the not only SQL is what our meaning is. And the problem that I have when I go into companies is that many of the things that I was doing back in the 80s, when I worked for ETA Systems, I was trying to get the cost per CPU hour down to about $7,000 an hour. And what we now see is if you go into Google and look at their data centers, they have racks and racks and racks of these low-cost commodity processors. And what they have figured out how to do is carve up their problems so that they are repurposed as a series of small transformations of data that can be done independently of each other. Right? And we call that functional programming, or MapReduce is another system. And the key thing about it is the cost per hour is dramatically less. So this goes into the core of what we've been taught through the very beginning of our computer science education. Most people have heard of von Neumann computers. You know about program counters. You know that in Java and JavaScript that you can say x equals x plus 1. Right? That's kind of inherent in our thinking of what computer science is. There's another way of looking at it. And that's where you can never do x equals x plus 1. And that's functional programming. Functional programming is everything is a function where the output is completely determined by the input. And if you think in that way, you can do a hash of the input, store the output of that hash in your cache, and really change what you're actually doing with computing. As an example of the difference of this, I encourage you to go to the Amazon website, and I encourage you to look at what the price per hour is for an elastic MapReduce server, and compare it with what if you needed your own dedicated server where you could do x equals x plus 1 and be safe that the results would always be consistent. All right? And the answer is that Alonzo's way of functional programming, of MapReduce, of distributed transformation is about 75% less. All right? 75% less if you rethink the way that you're solving your problems in the terms of distributed transformation of data. All right? Now, I don't want you to go to your management and say, I can save 3/4 of our IT budget, because converting your organization to think in terms of transformation of data is a non-trivial event. Right? How are you going to do transactions? How are you going to define web pages, and how are you going to build those together? Those are all important things that you have to think about when you're making this transition. But many organizations that are competitive, that need to have these services, need to rethink those things. So you've probably heard about why NoSQL has taken off. There's the 3 V's: volume, data velocity, how fast the data is coming, and data variety, how many different types of data. And in our book we talk about those, but we also go on a little bit more. We have to give credit where credit is due. The people that have been building OLAP and BI and warehouse, they left the SQL world a while ago. Anybody here use the language MDX? So MDX is a variation of SQL, but it's really designed for slicing and dicing data. And in fact, who created it was Microsoft. Microsoft did this quite a while ago. So they left the safe, secure of NoSQL world. They made small changes so that they could do that slice and dice. And a lot of these other pressures have caused people to leave that world and go into the NoSQL world. The other thing I have to really emphasize is that when people are coming to me, they don't just have general ledger data anymore. They have transactional data, they have data warehouse data, they have log files they want to analyze, they have Internet of Things sensor data, They have read-mostly data. They have binary data. They have images. They have videos. They have sounds. They have PowerPoint documents. They want to be able to do a query that says, of all the people in our company, give me a ranked list of everybody who's a solution architect that has done at least one slide with the title NoSQL in a title of a PowerPoint slide. And that's going to be a sorted list based on how many slides they've done, right? Most people can't do joins between titles of PowerPoint slides, but these new NoSQL databases are allowing you to do those. So open link data is a big thing. JSON is a big thing. XML data and documents, like what MapReduce is doing, is a very good example of that. The other thing about this data is that people have a variety of different uses of the data. So it's a blooming kinds of data, but then you're also not just doing transactions and analysis. You're also doing search and findability. As we get more and more data, finding things becomes more and more important. How many people here use something called SharePoint within your organization? Okay, almost, probably 2/3. How many people think that SharePoint search is really great in your organization? Okay, and there's a reason. A lot of times when you set these things up, they set up these folders. And if you're trying to narrow the search, if you don't think that people are storing it in the right folder collection, you can't narrow it down. All right? So some of the NoSQL systems take all of your SharePoint documents, look at all of them, look at all the keywords, and automatically classify them in multiple containers based on the keywords inside those documents. All right? And then they're stored in a MapReduce or another document database. And what happens with those organizations is the satisfaction for findability and search goes up dramatically. All right? And the other thing is, if you have a document, it can also find similar documents. So the concept of keywords and vector spaces and document similarity goes up. If you don't have one database that does a lot of those things, you're going to be struggling to try to put things together. All right? Enterprise agility, a huge thing, right? The fact that I can take massive amounts of XML data, and some of the people over at the BCA are probably dealing with loss, where you have huge amounts of XML and you just load it up without ever modeling it. And if you get different types of data from different other partners, you don't have to model that. You can still store it. And so we have enterprise agility in storage. Discovery and insight, where you're trying to find patterns, is important. Speed and reliability, and then consistency and availability, where you have many replicated clusters, and those clusters store documents in multiple places. If one node goes down, there's other places. All right, so how is this really happening in some of these organizations? I always go back to the 1970s, 80s, 90s, where I was doing a lot of SQL programming, and it seems like most of my job was to do ETL out of one silo and move it into another silo. And that was very frustrating, and it was minimized when companies went to these ERP systems, right, where they took all these silos, put them in one relational database, and they started to complement. They didn't have to necessarily search that operational system. They'd dump the data out every night into their warehouse, and they could do OLAP queries and things like that. But the problem with that is that the documents still were a second-class citizen. They say 80% of the knowledge in an organization lives in documents and not in your ERP systems. And they couldn't really connect those together. All right, so now we're seeing the next stage. And the next stage is we're not replacing our ERP systems with NoSQL. We're not replacing our data warehouse. What we're doing is we're adding another system, NoSQL servers, and documents are primary citizens in that searchability and that ability to do joins between those systems. All right, so it's a complementary structure. It's a new system. It does require new skills and new DBAs and new administrations and new reporting and new architectures. The other thing I want to talk about is simplicity. All right, one of the things that many of the most innovative companies in the Bay Area are doing is they're throwing out all the old constraints. They're not making them compatible with SQL to start out with. Maybe they're working on high availability or in-memory management or using solid-state disk. And to keep things really fast, they strip out everything except what they need to solve a specific type of business problem. And that simplicity allows those databases to do other things. There's three important papers that a lot of the NoSQL technologies are built on. The first one I always like to brag is Jeffrey Dean. Jeffrey Dean is a graduate of the University of Minnesota here. He's one of the people that co-wrote the initial paper on MapReduce. And I should mention map and reduce are simple functions that you can get in any programming language. The challenge is, how do you do it at scale? How do you do 1,000,000 transformations, and if any of the nodes that those transformations are happening on, how to recover it and make sure you're getting consistent results? Another important paper also came out of Google, which was also written by Jeff Dean, which is not about how to transform the data at scale, but where to store it and make sure that that storing can scale. And that was the original Bigtable paper. And this is what all of the Hadoop HDFS databases are built around, that column family store. So that's there's a lot of good things that I would strongly recommend reading. The third most important paper actually didn't come out of Google, but came out of Amazon. This is Werner Vogel's, and this is his blog. On October 2007, they released one of the most important papers on Amazon DynamoDB, which at the time was not available outside of Amazon. That's one of the reasons Target actually probably moved their system to Amazon for a while, because they had a system that was both highly available and highly scalable, even at the worst times of the Christmas year. And what they did is they had a huge cluster of nodes that were all voting on whether or not each other was reliable. And just like we had Survivor where you vote somebody off the island, they would vote people out of the cluster if their data wasn't reliable and accurate. Right? Most systems didn't have those algorithms. The DynamoDB paper had those algorithms. It talked about them. It even described how they worked. And many of the NoSQL systems are what they call Dynamo-inspired systems. Cassandra is an example of that. Aerospike, Foundation DB, all those things. Remember, Amazon had unlimited Oracle licenses at the time. They had unlimited Oracle consultants on staff. And yet they still said, we're not going to use a relational database because it can't be reliable and it can't scale to what our requirements are. All right. The other thing about NoSQL systems is that we have to seriously think about not scaling up, but scaling out. When people talk about scaling up, they think about taking a single core processor and tweaking it a little so it's a little faster. Maybe you get a faster clock rate. Maybe you put a little bit more RAM. Maybe make it faster RAM. Maybe give it additional disks. But the problem with that is that around 2005, we realized that the heat that dissipates from a standard chip has limits, has physical limits that it can leave two-dimensional silicon. And we call it the power wall, right? Clock rates used to be increasing every couple months, but around 2005, they stopped increasing, or you could increase it a little, but you had to put it in liquid nitrogen and do huge things, and you'd get a 5 or 10% increase in clock rate, right? Because of the power wall, the NoSQL community said, we are going to focus on cost-effective computing and not on a single processor. We're going to figure out how to divide and conquer our problems by breaking it into small pieces that we can then fan out to these processors, have them each analyze their own data, transform it, and write it their own local disk, and that's called scale-out. Right? And the book has a lot of examples of case studies of companies that realized that to be competitive, they had to master the art of scale-out. One of the things about these clusters is that they have a feature called auto-sharding. Now, a lot of people are familiar with the concept called replication, where you take your data and you make copies of it on another node, so if the primary one fails, a slave will pick up. Auto-sharding is not that. Auto-sharding is when one node gets too busy, it signals, I have too much data or I have too much processing power, and it automatically can signal a system, and you can have an administrator get in the way of this or not, that it's going to take its data and it's going to partition it into two separate nodes, and it's going to do this automatically in the background, and then it's going to flip a switch, and that the new read requests are automatically going to find their ways to those new nodes. And they have all sorts of tricks to do that. If you're familiar with a hash function, you take a URL, you run it through your hash function, you take the leading bits, and that's an algorithm of where to find it. And all these NoSQL systems using these hash mod tricks to place the data consistently on the right nodes, but if nodes fail, if they're added or removed, they all know how to recover from that. These systems do this almost automatically, and that means that your operational overhead of having to hire somebody to build and configure a new system and take half your data, do it manually, which in some organization I work with would take weeks, can now be done in minutes. Now, it takes a while to copy this, but the switchover happens almost transparently. One of the other things that you hear in the NoSQL movement is this idea of schema-free. And this term should be kind of used with a little bit of quotes around it, because there are always schemas in the world. Somebody designs schemas. At the federal level, if I'm doing National Information Exchange Model, NIEM, the NIEM people designed those structures in the past. But the problem with a lot of the data exchanges that I did at the federal level was that versioning was always a problem, where we get new elements are added or elements taken away or elements moved around. And with a lot of these enterprise messaging systems, I could deal with multiple versions as long as I didn't have to model them all and store them all in rigid tables. So schema-free is really the concept that the database uses the knowledge around the data, those XML tag names, the JSON labels, and based on that, it builds the structures to automatically retrieve it quickly. Now, this doesn't say it automatically builds range indexes and all these other things. That's often an additional process, and the tools are smart enough that they can suggest range indexes. But schema-free means that it's an ideal system when you have enterprise messaging to go into these NoSQL databases, and there are plenty of case studies about this. Craigslist is a really good example. Craigslist actually uses a relational database as their front end, but a NoSQL database as their archive, because they've changed their database over years, and they're still required by law to be able to pull back old things, but they're not going to put it in multiple versions of relational database in the archive. It's all stored in one NoSQL database. All right, so when we talk a little bit about horizontal scalability, I want to mention that this is something you can measure, and usually measure without having to buy an entire cluster. Right now, there are many tools that you can set up a cluster on Amazon Web Servers. You can create tools that will simulate loads, number of reads or writes per second. And a lot of the customers that I work with will just get a 10 or 12 cluster node, simulate tens of thousands or hundreds of thousands of reads or writes per second on their system, and make sure that as they add nodes, they're not slowing down. Now, you do need to understand a little bit about how Amazon disks work, because disk and network I/O can often be the bottlenecks. But what our goal is to have what we call linear scalability, that as you add nodes to the cluster, you're not going to get some point where the scalability goes down. Every time I go into organizations and they try to do complex joins between data sets, sometimes they hit these non-scalable things. So designing your systems so that you have native document things and document modeling, and you can still do some joins between it, but you're going to reduce those to cached lookup functions. Those are all things that we want to work on when we design for scalability. The other thing is lowering cost. All right? NoSQL systems are different because they simply don't use these storage area networks or network attached storage, because they always seem to become bottlenecks. And why is that? Everybody's probably familiar with this concept on the left of shared RAM systems. We have some case studies in the book where we have graph solutions where graphs tend to have to be in shared memory when you're doing graph traversal. And that's kind of the exception to the rule. But shared disks often means that when you're doing transformations, you're bringing in huge blocks of data, running a transformation and writing it. Those shared disks become bottlenecks, and they become very, very expensive. And they try to configure them with striped RAID and all these things to get throughput. But the bottom line is the cost per gigabyte is usually pretty high. The way you keep your cost per gigabyte very low is to buy commodity processors, not necessarily inexpensive, but uniform processors that each have their own CPU and RAM and disk, so that when you do a distributed query, their queries are going out to each of the data nodes, they're running through its local copy of data, they're doing the transformation backup, and only the reduced data set is sent back to the users. All right? So that shared nothing is really the best way to get the lowest in cost per gigabyte. All right, the other thing to think about is the fact that many of the most modern what we call almost second-generation NoSQL systems, have gone away from the model on the left, which is master-slave, and moving toward the model on the right, which is a true peer-to-peer. Some of the older systems with master-slave, MongoDB is a classic one where they have one node that intercepts all the reads and writes and then distributes it to the other nodes. That usually becomes a bottleneck, and it is certainly a single point of failure. There is something called a standby master you can use, but the problem is it's very difficult to test flipping over to a standby in a production system. All right? So testing your failover is complicated. A much better architecture is to have every node in the cluster have all of the information it needs to distribute both read and write queries to every node, using hash mods as an example of that. But each of these nodes then has to maintain a little bit of data about where to send and read and write those systems. So the most modern systems are all moving to that, and they have both high availability and much lower operational DevOps costs doing this. All right, so when you start to build these systems, I always go back to the old radio kits that I used to build as a kid, where we had these rows of knobs for bass and treble. And I always try to think about when you build a service for a customer, you want to be able to tune it specifically to support the number of reads and writes per second for that service. This is difficult to do when you have one relational database with 500 tables and 1,000 users all doing different queries. Can you guarantee that a query will return in 20 milliseconds when you have a lot of other things going on? And the answer is you usually can't. But with these NoSQL systems, because you have small, inexpensive commodity processors, you can configure a small cluster or a piece of a cluster and have the right amount of replication, which maximizes reads, or have a lot more system to optimize write per second, maybe adding more memory or more solid-state drives, or change the number of duplicate copies by adjusting all these knobs, and whether you're going to send it to a remote data center or guarantee transactions. These are all things you can configure in these NoSQL databases. And the net result is, once you adjust the knobs, you'll be able to figure out how many processors you need, and you can adjust the costs. And you can work with your business unit to have fine-grained cost control. And there's a lot of examples out there when you configure your web services to do that. All right, so for the last 15 minutes, I'm just going to go through some of the key NoSQL architecture. We're going to talk about what they're really noted for and what examples of them are in the marketplace. So key value stores, as I mentioned, is the simplest data model. And everybody who uses a file system knows that given a file path, you're going to associate a blob at that file path. So file systems are examples of key value stores. The World Wide Web is an example of a distributed key value store. What's the key? It's the URL. What's the value? It's the page that sits at that URL, and it can be HTML or PDF or a combination of JavaScript things. And the key thing about that is, because of caching, it allows you to fetch images once and not have to fetch them again when they're in your local cache. Right? So if we learn those things, we can apply those same things to databases. Many of these in-memory systems put those things in memory once they're queried, and a lot of other databases now add this as a front-end layer. Examples of this are Berkeley DB, Memcache, Amazon Dynamo, Amazon S3, which is a distributed, technically an object store, and then Redis and React are other examples that start with that. This is where most NoSQL companies start. I know that, for example, the latest ones, Aerospike and Foundation DB, are new startups, and they've been rewritten from scratch to take advantage of nothing but solid-state drive. You just don't use spinning disks as much for their things, because a lot of them are very low latency and very fast. They are very scalable. They have simple APIs. But the problem is there's no way in the base versions that you can query the value. Now, I should also mention Redis has changed that. So they give you sets and things that they index things within the values. So they've kind of tweaked the values so that you can in fact, store sets and query values of sets and lists inside of those values. So they've gone away from that pure key value store. A variation, but very similar, is that column family store I mentioned, where we have a row and a column, Cassandra, HBase, Hypertable, which we don't see much anymore, Apache Accumula, which adds a 64-bit visibility field for high security, and Amazon's Bigtable. And I should mention that the keys for column family stores can get complicated. All right, and it's not just a row ID, but sometimes they have a column ID, just like a spreadsheet may have a row and column. And then they group columns together in a family. So you can get clusters of things together, so all the columns in an invoice can be grouped together. And you still can't do joins on these things, but there is much more data modeling that you do, and you do have to think about the schema and how you design these systems. Also, column family stores almost all have timestamps. So you can do versioning. And by default, they have 3 versions. And if you want to go back and look at a previous period of time, if you have enough versions, you can do that. All right. Graph stores then are kind of the oddball. This is the one thing that doesn't scale out, and it works best if you store the entire graph in memory. But programs like Neo4j, Allegro Graph, Infinite Graph, Stardog, which is being used over at Best Buy, those are all different ways of storing triples and graphs and doing queries on those. And these are really good when you're doing social networks and you want to take a subset of all your data, put it in memory, and do analysis and discovery in that. They don't tend to scale well if you can't fit it in one. They do have different representations, and RDF and Sparkle are the query languages for those. Last one I want to mention is document stores. And document stores is the one that I've been using the most. This is the one I first started using in 2006, where we're storing data in nested hierarchies. MarkLogic, Mongo, Couchbase, CouchDB, which are completely separate products, I should mention now. RavenDB and ExistDB are all example of document stores. And the nice thing about these is that you can store entire JSON or XML documents without having to do any work on the database. It just absorbs it and does it. It's also ideal for search, because if you retain the structure of these documents, you can boost the search rank based on where in the document you find them. The problem is they're relatively complicated to implement, and the open source solutions aren't as robust. The commercial solutions really do have that robustness. I just want to mention structured search. Anybody who goes to your SharePoint site, types in keywords, and thinks you can find your document, and it is there, but it's 10 pages down in the search hits, knows that what SharePoint does is it takes all the words out of a document, counts them, puts them in a bag, and then just tells you, without a ranking, that those documents have that word in it. The problem is if a word occurs in the title of a PowerPoint slide, or in a chapter heading of a book, it doesn't have a higher rank. There's no way that you can easily do it. There's ways you can manually go and extract them, put them in a separate thing and say, here's the titles and here's the keywords. But in general, most SharePoint administrators don't take the time to do that. All right? Retained structure search means that every time that I put these XML documents or JSON documents, I give it a different boost ranking based on where it appears. So it appears at the title of a document, in the abstract of a document, in the chapter heading. It'll have a much higher rank, and so people get much higher relevancy and precision when they're doing search and retrieval tools and that. All the metadata registries that I build, people want to find the data on the first page. If they don't find it, they put it in the registry again, and then you get duplication, and then all hell breaks loose. So findability and metadata registries are really critical for why I did this. So what it means then is every node in your document is its own document. It has its own document ID. And when you do a search, it knows exactly where in the document it appears, and you can tweak the weighting for that. All right, so let's wrap up. So this is about architecture. All right, there's a guy over at the Minnesota Office of the Revisor named Isaac Homeland. He was trying to store statutes in a relational database, and he said this is what it felt like to store highly structured documents inside of an Oracle database. He said once he learned about native XML, this is what it felt like. There was nothing in the way. He could load the documents, he could search them, he could transfer them. Nothing got in his way. It was all about picking the architecture that fit the problem. And this is what I want people in Minnesota to be good at, is knowing all 6 of these architectures and knowing when you have a business problem, what's the architecture that will solve the problem right. This is an important question because there are a lot of jobs in Minnesota that are going to California because in California, somehow they figured out all 6 of these architectures are important. Granted, they were being pushed by the social networking world. They were being pushed by the search and retrieval world. But in Minnesota, we still have a lot of catching up to do. We're not teaching most of these patterns in our classes. We're not teaching them in our enterprise overview. We simply are doing the same thing over and over again. And I can give you a list. My wife and I have a list of the cognitive biases that we encounter over and over in big companies. And they're making decisions based on what license they've paid for, what training they just sent their DBAs to, what they think the CIO wants, and not what's right for the customer. And that's too bad. And I'm really hoping that people will get a chance to take some time to look into NoSQL. If you can get the book and give me feedback, I'd love to do it. Our job is to make sure that enterprise architects in the Midwest give everybody a fair shake at using the right architecture and grow their business in a way that I think is fair to those businesses. So, all right, that's what I was going to cover. Any questions? Yes. No.
So early on, you said I had all this stuff I was going to do back to the state, and all the 200 some odd elements I'm going to shove into a relational data store, PA, OEM. Many of us still have that problem. Are you suggesting that NoSQL is a viable alternative to that problem? So if I'm going to collect lots of data about my consumer, regardless of how we define consumer, preferences, account information, blah, 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 blah. Shove it into my relational database, and I have to go through many layers to get to it. All kinds of energy making those layers, and I can instead say, not so much. I'm just going to go there.
Yes, that's exactly what I'm saying.
That's intriguing.
I did a project with grantsolutions.gov. They had roughly 10,000 business forms for applying to federal grants. And they could all be stored in a native XML database without ever modeling any of the data in any form. Okay. I think doing that same, and make it searchable. So if I had a social security number in any form of any document that they collect, I could search, doesn't matter what level it was nested down, / social security number, they could do it. I could run reports that find all personally identifiable information in any forms to make sure that the right security policies get applied. So those things are very critical.
So the keyword there was searchable. What if I want to do transactions updates?
Most of the commercial NoSQL products do support transactions at some level. MarkLogic certainly does. And they use something called MVCC, multi-version concurrency control, so that every time you make a change to a document, it keeps the old one and keeps the timestamps. The bottom line is it's easy to undo those operations if transactions fail. So it's a fancy way of doing versioning with timestamps. Another question over there.
Yeah, another question around the transactional workloads. How many companies, or what % of companies would you say are using NoSQL databases to support something like, say, a contact center, a customer contact center, which traditionally in the past has been supported by relational models?
It depends on the part of the country. In Minnesota, we have a new MarkLogic system going in at the BCA for their criminal history system. We have some MarkLogic systems over at Thomson Reuters. But in general, we are talking about a dozen companies that are using NoSQL in Minnesota. In the Bay Area, it's flipped. Almost all of them are doing that. And a lot of it is driven by software vendors, right? And here's the challenging thing, is that some software vendors have made the leap. They want to provide a solution that, and you shouldn't care about what database that runs in. If the solution is flexible and is going to manage your contact center well, they can do it. The problem is that software vendors take a couple years to upgrade their databases and new software vendors to come out. And so there's a lag time between when a solution is available and when the raw databases are there. What I can say is that there's a huge amount of money into new startups that are doing things like contact centers that are no longer using the relational model that are going to the NoSQL model for a lot of their products. But it'll take time.
You had mentioned the join limitation there. Tell me a little bit more about the join limitation, because oftentimes those contact center systems are trying to bring things together to answer a question. Where does it start to fall apart with the join limitation?
So that's a good question. When I think of a contact center bringing diverse data sets together, I think of maybe a call center, web logs, all the touch points that a single customer has had with diverse parts of organizations. The biggest thing about that is you'd have highly variable different types of data. And the NoSQL systems that I'm working with allow those systems to be all grouped together inside of a customer's thing, regardless of the structure of where it came in. One might be, well, they visited these pages on the website, and so here's a history of the pages they visited. They called in and talked to this operator at this time, and here's the notes for that. And all of those would be displayed once you brought up the customer record. The problem with integration and relational is that you have to force it into something that has been pre-modeled, that has been modeled beforehand. So as you bring new data sources online, sometimes it takes you 18 months to get a whole project, to get a data modeling team to model it, to figure out the best fit. And then if they make changes, it's not going to work. The NoSQL world is much more about gathering ad hoc data, unstructured data, clustering it all together, giving you very good search, and then displaying it all in a way that somebody can still read it and then see the history that you had. So the time and the problems are the integration with old models, not can you ingest new data. The biggest differentiation is what we call agile ingestion, where there's simply very little time between dragging and dropping the files in the folder and seeing the results on the screen. Okay. All right. Well, thank you very much for coming.